Hi, my name is Meng Fanchen, and today I'm going to discuss first principles calculation and its use in studying novel carbon materials. Understanding the electronic structures of these carbon materials will allow further research into the possible application of these carbon-based materials and possible discoveries of new carbon allotropes. First principles is a method used to calculate the interaction between atoms and molecules on the atomic level. Due to the use of first principles, electronic behaviors of molecules, surfaces, and bulk materials can be studied, and predictions could be made. The energy consumption or release of a reaction and the likely occurrence of the reaction could also be predicted. This allowed the study of atomic interaction without the need to construct any experiments. So, what is the benefit of using first principles? Well, there are several advantages to design an experimenting material and even the materials not existing at the moment, and calculate their geometric as well as electronic structures instead of an actual chemical laboratory. First principles calculation allows the design of a material and deep study of its electronic behaviors without having to physically create the chemical prototypes. This lets material and physics research be done for much lower cost and allow more research to be done and more discoveries to be made. As the electronic structure determines the macro properties of a certain kind of material, first principles calculation also allows us to predict the potential application of this material. Sometimes experiments may find it hard to explain some micro behavior of one material, but a deep analysis of the electronic structure will help the explanation and allow research that was previously not possible due to the cost or due to the chemical limitations. First principles calculation is carried out using a standard set of computational tools. There are a few types of background experience that helps prepare someone for doing this kind of research. Now, Linux operating systems and general computer knowledge. Also, knowledge of programming and other forms of computer experience. All these are helpful background for doing this type of research. The focus of my research is to calculate the geometric structures and electronic structures of non-existing carbon materials, and to predict whether or not they could exist steadily. First, I will talk about the zigzag of graphene nanoribbon. Previous research found half-metallicity feature in which one spin channel is conductive and the other is insulative could be achieved by a transverse electrical field, and that the half-metallicity in zigzag of graphene nanoribbon operates with the characteristics of the anti-ferromagnetic ground state. However, I noticed that the energy difference between anti-ferromagnetic ground state and ferromagnetic metastable state is very small, and under room temperature, anti-ferromagnetic state will be turned into ferromagnetic state. So the half-metallicity would be destroyed, and the potential for zigzag of graphene nanoribbon to be used as electronic devices would not be achieved anyway. Then I proposed the dehydrogenation for zigzag of graphene nanoribbon and examined the energy difference between the anti-ferromagnetic ground state and ferromagnetic metastable state, which is increased by almost 1 order, leading anti-ferromagnetic ground state to be stable under room temperature. Also, I found the dehydrogenation effects on band structure of zigzag of graphene nanoribbon and the change of magnetic moment of each carbon atoms. Both could help explain the increase of the energy difference. Fullerene is another novel carbon allotrope I'm interested in. After talking with our university's honorary professor, Sir Harold Croto, I found exploring the smallest fullerene is one of main focuses of scientists relevant to fullerene. After consulting a lot of references, I learned that smallest fullerene in theory is C20 and Gi at C28 in experiment. This inspires me to test whether or not C20 could be stabilized by encapsulation of a metal atom. First, I calculated the electronic structure of C20 and found it is an open shell system. And noticing that it has 20 valence electrons, the traditional 18 electron rule could not work. Then I turned my focus to 32 electron rule, in which F electrons are involved. In this way, I set my focus on lanthanide and actinide atoms. All the atoms in the rectangle are involved in my calculation, and I employed binding energy, dissociation energy, and homo-LUMO gap to characterize their stability, and make my prediction that YB, LU, AM, NO, and LR atom could help stabilize C20. That's all for my presentation. Thank you very much.